Let's do an example of mutual inductance. So we have a 2.44 meter long coil, has 255 loops around an iron core, so we have multiplication factor for our mu naught, and it's with a second coil of 115 loops, and they're wound around a radius of 2 centimeters. And if the first coil drops uniformly or linearly from 12 amps to 0 in 98 milliseconds, we want to know the mutual inductance and the EMF induced in the second coil. So there are a lot of given quantities here. The length of the coil is 2.44 meters. It's a long coil. Our turns in coil 1 is equal to 225. Our mu value is equal to 1850 times mu naught. The number of turns in our second coil is 115. The radius of the coil is equal to 2 centimeters. Our initial current is equal to 12 amps. Our final current is equal to 0 amps. And our time for the drop of current is 98 milliseconds, or that's 0.098 seconds. So we'll start with A, the mutual inductance. The first thing we need to find is the magnetic field based on a solenoid, and that's going to be mu times N1 times the initial current divided by the length of the coil, initial current is 12 amps, divided by 2.44 meters, and we calculate that to be 2.573 teslas. Our flux is going to equal our magnetic field times pi r coil squared. And that's going to be equal to 3.233 times 10 to the minus third, and the units for the flux is Webers. It's spelled W-E-B-E-R-S, Webers. And our mutual inductance is going to be equal to N2 times our phi divided by I initial and that's going to be equal to 115 times our Webers for the flux over the initial current, which is 12 amps, and that gives me 0.031 henries. That's the unit of inductance. So that's our M value. For B, our electric induced potential in coil 2 is going to be minus M times the current, and this is the slope, so it's going to be I final minus I initial over T drop. That's going to be, forgot a 0. Seconds. And that gives me an induced voltage of 3.793 volts.